Let's get started. How's everyone doing? Come on, let's do better than that. How is everyone doing? Thank you. Welcome to 3091. This is the first day, and I'm really excited. I hope you are too. In this very first lecture, we're going to do a little bit of administration, tell you a little bit about the class and how it's set up. And then we'll give a little we'll have time for a mini lecture in the second part of the lecture today. So I thought I'd start by introducing me. My name is Jeff Grossman. I am in course 3, that's the Department of Material Science and Engineering. My background, I went to Hopkins undergrad, moved my way towards the West Coast, Illinois PhD, and I did a postdoc at Berkeley. And then I came here to MIT about 9 years ago when I joined the faculty. My own passion, my own interest in research is in materials for energy and water and chemical processes and separations. So I thought I'd just give you a little example of what I mean by that. So I get really excited about the ability to take a material and make it do something that it can't do now, but that it needs to do to solve a problem. Maybe it needs to be cheaper, maybe it needs to be more efficient, right? So one example is in this material. This is a barrel of oil. And what we do today with this barrel of oil is we mostly burn it. A lot of what we do is we burn it. Now, if you do that and you think about it in terms of energy, that's 159 liters of this material. And if you think about what you're caring about as energy, you get 1.73 megawatt hours of energy out of that. But see, I like to think about materials again and ask them what they can do differently for me for these problems. And so if you think about that and you say, well, okay, let's just take 1% of the carbon in that barrel of oil and do something with it. Let's make thin film solar cells, right? Well, if you do that and they're not very good, they're 5% efficient, they completely die in a year, you get 10,000 times as much energy over that year than burning it. So it's an example of what you can do when you think about using elements differently. That's what I get really excited about in my research. And that's just one example. You can go, you can take that same carbon and you can make a thermoelectric that's on top, or you can make the world's thinnest filter. That's a piece of graphene with a hole in it. And that's still working with just one element, carbon, right? So there are many, many things you can do once you understand what these elements are and how they combine together. And that's what we're going to talk about in this class over the fall. How many elements are in your phone? We just talked about one element. Anybody know how many elements are in your phone? How many? Take a guess. 7. 27. Okay, it depends. It depends. Do you have the Samsung? If you got the Samsung whatever, it might light on fire. If you got the newer one, it won't. Do you have an iPhone? But you know what? In the iPhone, there's 63. 63 elements. Right? So we have these lectures in course 3. They're called the Wolf Lectures, and I gave one a couple years ago. If you're interested in hearing a little bit more about what I do or what some other people do who think about materials in this way, you can just Google Wolf Lecture and you'll get to some of the videos. And I'll mention it when they come around during the year. Okay, so that's a little intro to me. What about the class? So as I said, at the heart of the class is kind of what I just described. But in order to do that, we need to know some very basic things. We need to know how atoms are arranged, right? The atomic arrangement right there. We also need to know what atoms are there in the first place. But if we know that, if we know those things, then we can build. Right? We can get properties, we can get structure, we can get processing, we can get performance, and we can talk about how all of these things relate to each other. They're all correlated. If I change the processing of something, I change the properties. How do you know how it changes? Well, you got to know these things. And at the core of it all is really the thesis of this class, which is that the electronic structure, we'll be talking about this, structure of the elements holds the key to understanding. That really is what this class is about. holds the key. The electronic structure of the elements holds the key. That's what we're here to talk about. And the first part of this class is really the basic foundations of chemistry. Right? And some of you may have seen some of this before. We're going to build these elements. We're going to talk about them. We're going to learn about the electrons and the electronic structure. But then we're going to make solids out of them. And we're going to talk about what those do and how the chemistry relates to the solids and to the properties of those solids. Right? Now, I want you to know, again, this is a sort of administrative introduction. Right? You are not alone. On this journey, you have many, many resources, and we are here to help you learn this material and do the best you can, right? So first you have me. You have your TA. I'll talk about them in a second. You have Laura. Where's Laura? Oh, we're going to talk about Laura in a second. You have the textbook and the internet. I hear there's stuff on the internet. And you have each other. And I really want you to work together. Thank you. that hit me right here, right in the first 10 minutes of class. So the textbook is Averill. It's a really good textbook. Please use it. Please. Right? It's available here. Notes, like I said, will be posted on the same day of each lecture. I will post whatever you see on this screen. I will post. All right. Good. The goodie bag. So the goodie bag is another part of your homework. And these will be given out 9 weeks, right? So sort of like the quizzes, right? And in each goodie bag, which I'm going to talk about in a second, there are things to do. This is a hands-on complement to 3091 lectures and all the other materials. Now, these goodie bags are really important. And one of the 2 quiz questions, every week that there's a quiz, there are 2 questions. And one of them will be directly related to something that you're supposed to do in the goodie bag. And in fact, we will most times ask you to bring something into the quiz that is in the bag. So don't throw it away, and please do it, because one of the 2 quiz questions will be very related to the goodie bag, and the other will be related to problems, lecture. Everything's related to lecture, right? But at least one will be related to what's in the bag. So we really take this seriously. This is a very important part of your homework. And, there it is, some of which you need to bring to the quiz. And we'll tell you what that is before the quiz. I want to tell you a thing, though, because here's the thing. When, goodie bags it's a little bit of, what's going on here? This is a lecture class. Why are we getting goodie bags, right? And it's because I believe in the soul of MIT. I believe in the soul of MIT. And that is that we learn best by thinking and doing. And even though this is a lecture class, I still want you to do. I want you to have stuff in your hands so that you can play with the chemistry that we're learning about. Now, this goes back. I said the soul of MIT. What do I mean? This goes back. All the way back to before MIT was born, 1850s. You got a group of really smart people. They're getting together and they're meeting and they're saying, okay, we're going to start up a new university. What should we do? And they wrote out a plan. And it's called the Institute Plan. That makes sense, 1860. It's a great read. But I want to pull out one part that's really important. That what they wanted to do with this great new institution was to do something that would serve the interests of the commerce and the arts, as well as of general education, call for the most earnest cooperation of intelligent culture with industrial pursuits. Intelligent culture, industrial pursuits. That is mens et manus. Right? Mind and hand. It's so important to MIT that we put it on our logo. That's how important it is. We don't put some animal on our logo. We put what matters. Mens et manus. We don't put the word truth. Veritas. I mean, I'm not going to name names. Harvard. But I mean, isn't that setting the bar kind of low? Like, were they lying before? I mean, I don't know. Look, honestly, I don't know. But what I know is that what we know is that, of course, the goal is truth. The difference is we know how to get it. Mens in manus is how to get it. Let me ask you a question. Why are you here? Not here in this classroom. I know you're here in the classroom because you signed up for it. Why are you at MIT? Why are you here at MIT? Right? I can tell you, you are here because you are some of the brightest, most gifted, most talented students on the planet. Right? Thank you. Whoever said that. Agreement. That was like a like online. But you are here because you want to use those talents to make the world a better place. Right? You are here because you know how to answer any question. But you are also here because you are going to experience a transition. You are going to experience a transition here. You are going to make the transition from knowing how to answer any question to knowing which question to ask. And that is the transition from student to scholar. That is MIT. That's mens in manus. Right? Now, it's not easy. You don't come here. Nobody comes to MIT to phone it in. Right? If universities were restaurants, this wouldn't be that fancy one where you go in and you order and then somebody cooks and brings you your food. This would be the one where we all go back into the kitchen and together we make the best meal we've ever had. That's the MIT way. That's the MIT way. And it's not about, you don't roam the halls here and bask in this reputation and think of it as some privilege to be here, because you are MIT's reputation. Freshmen, raise your hand. Yeah, there's a few of you. Starting today, you are MIT's reputation. Starting today. It's on you. So we don't walk around these great halls and feel privilege. We feel responsibility. That's what it means to be here. Okay? All right. Good. Well, now that we got that all straightened out, let's move on. That's the end of my administrative stuff. And with the last 20, 25 minutes, I want to do a little bit of an introduction to chemistry. And I'm not going to ever test you on history, but I want to just kind of get ourselves in the mood by going back, right? By going back. So I'm going to give you a little bit of history here in a few slides. Right? So we are interested in solid state chemistry because chemistry is that essential ingredient to understanding the natural world, and the solid state is the link between that and materials and engineering, right? That is the link. And so we'll talk a lot about this all the time. Ho ho. Come on out, Jerome. But where did chemistry begin? Okay, now, hold on. I got a pen? Oh, no, okay, that's better. I thought it was a pen. Where did it begin? Where did it begin? Well, people were mixing stuff a long time ago, but really, and there's some debate about this, the word chem itself, it may have come from Chem, the land of Chem, which means sort of the rich soil in Egypt, or maybe it came from chemia in Greek, which meant sort of mixing and pouring together. But the point is that what they were doing was they were taking stuff and making other stuff out of it. That dagger there is from ancient Egypt. It's from around 3000 BC. And the way they made that was by taking stuff from a meteor. It was iron and some nickel and some other things, but from a meteor. So they were able to make a really, really strong weapon out of it. They called those daggers from heaven. But the point is that what chemistry is about is it's about how you mix these things and what are you mixing in the first place? What was it that you took out of the meteor and why did it make that instead of that? How did I get that dagger? Right? That's really what this is about. And so if we go back to sort of the first people who really started discussing this, we start with Plato and Aristotle. And Plato had this idea, probably some of you may have heard it. So what is stuff made of? What is like the essence of things? They really thought about this and they debated it. And, Plato said there's four things. And some of you may have heard this. There's earth, right? There's fire. There's air. And there's water. And everything's made out of that. Right? Now, you can see that's a little limiting. Aristotle came along and said, wait a second, hold on. If I look out into the stars, they don't seem to change much, so there must be something else that's not, quote, earthly and corruptible. And he called that ether. But anyway, the point is, like, that's hard. It's hard to kind of explain everything with this. How are you going to build a world out of the... We can't even explain the Boston weather with just those 4 words. So it was limiting. But then along came these guys, Democritus and Leucippus, who was his teacher, and Democritus said, okay, look, there's something fundamental. So Democritus, he said, look, I believe there's something more than these 4 things. Democritus. And he said there are these things called atoms. So he was an atomist. An atom is indivisible. Indivisible. That's the meaning. Atomos in Greek. It meant indivisible, atom. And they fought about this. They fought about this a lot. And Plato, it said, was so upset about Democritus that he wanted all of his books burned. Back in the day, that was a serious diss. It would be like if I blocked somebody on Instagram. Can I do that? Is that a thing? No. Snapchat. What? I don't know. I was right. See? That's how big. I'm blocking you. Burn your books. Seriously dissing each other. Democritus. Now, it really happened quickly from there. A mere 2,000 years later, we get to modern chemistry. Why did it take 2,000 years? It took 2,000 years because we were missing something. So we had a lot of alchemy. And the thing about alchemy, there are actually some really interesting discoveries in alchemy, but they always tied it to something very non-rigorous. Like, oh, this works because of the phases of the moon or the tides, right? And so it really needed some rigorous way to study what things were made of, right? What things were made of. And that came, inevitable that might happen. Here we go. That came with the scientific method in the 1600s in Sir Francis Bacon. And I think a lot of you have seen the scientific method, but it was pivotal for chemistry. It was pivotal because it allowed people to think about this question of what stuff is made of, but using a rigorous approach, right? Make an observation, form a hypothesis, do an experiment, record. And that's what people started doing. That is what, for example, Robert Boyle did, one of the earlier ones, to think about things and talk about the element. They were all going back to thinking about these same issues. What are things made of? An element can't be broken down into 2 or more simpler substances by chemical means. So he was at that. He was going for that core. What is at the core? Oh, and then you had Priestley. Priestley discovered oxygen, and he did it by burning things. He did it by burning things. Just mentioning that word makes me want to put those on. And so he really studied combustion. he studied these reactions that were happening with oxygen and carbon-containing matter. It was combustion. So he burned stuff. He burned this. He burned that. He burned that. And he said, what happens when I do that? That was another way. Boyle played with pressure and volume, right? Pressure and volume relationships for gases. That was his way to try to get at what things are made of. Priestley wanted to blow stuff up. Oh, and he also worked with beer. He actually worked with beer, and he discovered that the same gas that comes out of fermenting beer is the gas that comes out of combusting. Okay, so you got a guy who's working on lighting stuff on fire and beer. And you can imagine maybe that wasn't going to be a good day at some point. And what happened is, actually, his experiments did, this is true, they slowed down when he fell into a vat of beer during one of his experiments. Now, the thing is, though, that he studied combustion, and that makes me think about combustion. And I feel like, this is a good time for my goodie bag, which is to illustrate a point. Oh, thank you, Jerome. Huh. That's going to some feed somewhere. Okay, now, the thing is that when you go to a restaurant and they have real candles, I get really happy about it. We'll tell candle stories later in the term as well. And this is what you're doing. You are lighting a candle on fire. Now, when you do that, you see, here's the thing. You're actually, I don't want you to think about it as lighting a candle. I want you to from now on, think about it as lighting C25H52. And in fact, if you go to a restaurant and you want to ask them if they have real candles, I don't care if you're out with friends or maybe you're on a date, raise your hand, ask the waiter and say, do you have any C25H52? And see if they know, see if they've taken some chemistry. What you're doing is you're doing that, you're combusting that fuel. Well, see, the whole world runs by lighting things on fire. You could light propane on fire, or you could light hydrogen on fire. And that's where we said, hands-on is a good way to learn. So let's see what that's like. There's the candle, which is tilting. I'm watching it. Really? Oh, okay. So, or you could light hydrogen on fire, and if you do that, this is what happens. Right? So, okay, let's do that again. These bubbles aren't, oh, I should have kept this on. There we go. That's really, really fun. But I'm going to stop. Oh, I'm not going to stop, because you just turned it on again. Now you're coaxing me to do more. Oh, these are bigger bubbles. These are bigger bubbles. Let's see if this gets a nice flame. Oh, thank you. There we go. All right. Okay. Now, that's my goodie bag for today. We run our world by doing this. I mean, not by lighting hydrogen bubbles on fire. But when you plug your phone in to charge it, you're lighting a fire. Think about that. You might not feel it. You are. No, I love that reaction. I love that reaction. You are lighting a fire. It may not be you, but somebody else is down the street at a power plant. This is how we run our world. We burn things. And so this study of combustion was extremely important, and it's going to be our first reaction. So what's happening when you light C25H52 on fire? What's happening is that you're reacting. You're doing, remember, Priestley discovered H52 plus oxygen. He discovered oxygen, and he also, remember, this comes off of beer too, he also discovered these other gases coming out, right? And that's the chemical reaction. Well, is it the chemical reaction? It's not done yet. It's not balanced. It's not balanced. Mass is being lost left and right. Not okay. Not okay. So we must, when we write down things that happen in chemistry like a reaction, we must find balance. It's also important in life, but it's very important in chemistry. And so if you balance this, right, you're going to put a 2, because here's the deal, and I'll talk about this more in a sec. C25H52 plus, anybody know how many O2s? 38, whoever said that, 38 is going to go to 25 CO2 plus 26 H2O. These are the kinds of things that are perfect to keep doing exercises on, through your problems, through your goodie bags, in your recitation. Right? These are exactly how did you do that? If you don't know, you will soon. You'll get help. Practice. Right? I know, I wrote this down. I'm just testing you. Well, I wasn't. I made a mistake. Because the 2 was supposed to go to the propane one, because I wanted to write that one, and I got excited, and I went to that instead. And that would be 13 O2, and that would be 8 CO2, and so on, 10 H2O. These are balanced. These are balanced. And balancing reactions is important. Why? Because it balances the mass, and it tells us something else. Once we count atoms, you'll see. We're going to count atoms on Friday. Right? But it's telling us that you can't just lose stuff. You can't just lose stuff. You got to have the same. Oh, and that, by the way, is what Lavoisier. Lavoisier. Where's Jerome? Oh, yeah. No. Shoot.
Isn't that butane, not propane?
Butane, not propane. It very well might have been. C4H10. Yes, I believe that is butane. Thank you. Oh, Jerome, come back. Jerome helps the class, and he helps my French. Lavoisier. No. Okay. Not. Say it. Oh. Lavoisier? Okay, I try. But now, he said, look, you got to conserve mass. You can't lose. You can't create or destroy matter when you do chemistry. When you do this, you cannot create or destroy matter. Okay? Conservation of mass, Lavoisier. It means that if you get a little more than that, so this is balancing. But you also can think about, whether you have anything, I probably should blow that. Whether you have anything, did you have too much, too little? Did I mix it just right? So like if you let's take another reaction, just as an example. If I mix iron and oxygen to make ferric oxide, oh, not balanced, 2, 3, 4. And I tell you, for example, that I've got 10 grams of iron reacts with, let's see, okay, I'm going to give it to you a different way. I'm going to say that it reacts with O2 to give 18.2 grams of Fe2O3. This is an example from the textbook. Then I know, because of conservation of mass from Lavoisier, that 8.2 grams, if this reacts fully, right? If iron reacts fully, it all goes away, there's none left. Then I must have, if I got 18.2 grams of ferric oxide, I must have reacted 8.2 grams of oxygen. That's conservation of mass. But there's another thing you can do with this, right? So I must have reacted 8.2 grams of oxygen. But there's another thing, because if I'd started, if I started now with 10 grams of O2 and 10 grams of iron, I'm going to have excess. I know that. I know that now. I'm going to have excess. And the thing is that there's something that's limiting here. What's in excess? The oxygen, because I started with the same amount of iron. There's more, but that means that we've got another term, which is that iron is the limiting reagent. You see that? Because now I'm limited, meaning this reaction goes and goes and goes, and something runs out first. That is the limiting reagent, right? And this was just done by thinking about Lavoisier's conservation of mass. I can't create or destroy atoms in a reaction. Not in this class. You take nuclear somewhere else, but not here. Here we don't destroy or create matter. Limiting reagent, balancing reactions, very, very fundamental first chemical concepts. Now, these guys were playing around with stuff and really trying to figure out, again, they're going back to Democritus. What are these indivisible elements, atoms? What are they? And all these guys were starting to mess with that. Once they had the scientific method, they were able to go very far. Here's Lavoisier's list, 33 elements. And he tried to organize them, and in some cases, he succeeded fairly well. Look at this. This is okay, where's Jerome? This is a tableau de substances. No, not even close. But look, simples, simple, fundamental atoms. What are those things that we're mixing together, that we've been mixing together for thousands of years? What is that thing I'm pulling out of this ore and making stuff out of? And he was trying to classify them using these experiments, right? And some of these are actually really were really good discoveries. I want you to experience this. I want you to go back to this time, and that is what the first goodie bag is about. So what I've given you in this goodie bag is the most accurate measuring device ever created and branded 3091. It's a ruler. I've given you 5 metal strips, and I want you to pretend that you don't know what these are. How do you find out? You do nothing with fire. Nothing. But I gave you vinegar. And you do lots with vinegar. Pour it on them. Measure it. Weigh it. Look at it. Shiny, not shiny. Different color. Densities. Think about what the differences are. Right? And I want to put you back in that time, and I want to make a point here. Goodie bags are not just about the questions I ask. I hope that you think even beyond the goodie bag. So if you use that vinegar and one of those things reacts, let's just suppose, with the vinegar, then think about what that is, and maybe vinegar is a test. Maybe it's a test, and you can react. You can pour vinegar and make reactions with other things. Maybe you should be thinking about where that thing is in the infinite corridor, and the whole infinite corridor should smell like vinegar. But we won't tell President Reif about that. But that's what I mean. Maybe not the infinite. But, explore. These are meant to be, I want you to really use these as an adventure. Think outside the box. So you've got this most accurate measuring device. You've got these strips, a pipette, and you've got some gloves. And that is your first goodie bag. Okay, now the last thing that I'm going to tell you about is why this matters. And just like the goodie bags, when I started teaching this class 3 years ago, I wanted to also protect a certain fundamental part of each lecture. And I call it my Why This Matters moment. Sometimes it goes on for more than a moment. But I really, really want every lecture to connect what we just learned to a big picture. Most of the time, it's some application or some global challenge, right? I want you to see those connections, that what you're learning is directly relevant to some big thing. So my Why This Matters moment is really related to these discoveries themselves, okay? Please give me till 11:55. I will always let you go on time, 11:55, but please don't start putting stuff away because it's distracting to everybody. So 2.5 minutes. We name the age we live in often by the element, by the atom, by the material. by the material that was most useful at the time. The Stone Age, the Bronze Age, the Iron Age. I would say we've moved through the Industrial Age, the age of plastics, the age of silicon. As a material scientist and engineer, I love this. I love that you name the age you live in by the material that mattered. But I also love that we will never do that again, ever. And the reason is that we live in a truly unique age now, a different age, one in which we can put atoms, we can realize Feynman's dream and put atoms anywhere we want. The question is not, can we make it as much anymore as it is, what should we make? We live in the age of atomic design. And that is really important. I mentioned the phone and the 63 elements. Look, this is called a revolution. This is called a revolution. You went in 50 years from $1 per transistor, 8 orders of magnitude cheaper. In 2012, it became cheaper to print a transistor on a chip than a character in a newspaper. That's a revolution. But that revolution, it started as a processing revolution with one really important element, silicon, and now it's a materials revolution with 63. It's a chemistry revolution. And the reason this matters so much, what are these things, is because so many of the problems that we face in this world today, so many of the global challenges, will rely on new chemistry and on new materials. Those are the bottlenecks. Those are the bottlenecks in cost and efficiency and processing, right? In properties. And those are the kinds of things that we're going to be talking about all throughout the fall. And that is our construction set. And we will build this on Friday. So see you guys all on Friday.